Hi, Grace.
Hi, Lindsay.
How are you?
I'm doing good. How are you doing?
I mean, I'm good because I'm excited that we're going to talk about math, which is one of my favorites.
Yes,
And we're going to
I
talk
am
about,
ready.
yes, you are. We're always ready, aren't we? And we're going to talk a little bit about like Schitt's Creek, which we both love.
Mm-hmm.
So good. Are you done watching the whole series?
I am. I recommend it.
Awesome. So yeah, definitely recommend that. And we're going to explore some data around people who like that show and like other shows they might like, and some studies that Netflix might want to conduct. So let's just do a warm up and then we'll recall some formulas and then we'll hop right into our worksheet. How does that sound?
Sounds awesome.
Okay, nothing like hanging out on a Friday doing some math. So let's suppose we have a bell-shaped curve and we are looking at, actually, let's just say it's the standard normal curve. And
Okay.
standard normal, what does that mean? What does that mean the mean is?
The mean's gonna be 0.
Correct. That's a standard normal curve. And then what is the standard deviation?
The standard deviation will be 1.
Perfect. That's a special curve where we've standardized all x values to be their z-scores, which means they say how many standard deviations away from the mean they are. Okay, suppose I want to look at this area. It's about here. We know from empirical rule, if you recall, that about 2 standard deviations away in each direction from the mean kind of block off. Do you remember what percent of the area is in here?
I think, is that 68%? Or is it 95?
95.
With
Yeah,
two.
because the first one is
Yeah.
68. Perfect.
Yeah.
So 95% of the area under that curve is there in the blue. And I drew my boundaries slightly in from exactly 2 standard deviations away from either side because I happen to know more accurately like the um the empirical rule says about 2. We're going to actually find that it's a little shy of 2 standard deviations away.
Okay.
Empirical rule was an approximation technique. So it was a little off, but it's pretty darn good. And so what I want to do is explore exactly what is this z value that cuts off that 95%. If it's not exactly 2, then like what is it? So if we have 95% of the area in the middle of this curve, what
Yeah.
percent do we have to share between these two tails? Like what percent is left
We'll
over?
have like 5% in total, right?
Right. So we'll have
Yeah.
5% left over. So I'm just going to note over here on the side that we're looking at the in-between area is 95% in decimal form.
Mhm.
So we have 5% to share between the two tails, right? Putting that in
Yeah.
decimal form. So how much is in each tail?
That would be like 0.025.
Yeah, 0.025. We'll label these later with something kind of special. For now, I'm just kind of keeping track of our work. And I'd actually like, now that we've split up that percentage, let's go ahead and say each of these is the 2.5%. Okay. Okay. How do we find, if our goal for this warm up is to find this z-score, and we know it's going to be about 2, so we're going to know if we got the right answer. How do
Mm-hmm.
we find a value along the horizontal axis, a boundary, if we know information about areas under the curve? Is there something that helps us with that?
Yeah, so that we can use like the inverse norm on our
Right.
calculator.
Totally. So the inverse norm function, z equals, that'll be inverse norm. Okay, now you and me, we're fancy like Alexis. So we have fancy calculators where if
Mm-hmm.
we go to inverse norm, yours does this too, right? Where we get to tell it the tail is either
Yeah.
left or right. Yeah, and so if you have in your calculator that's what you get to do. But any of the older calculators are going to require a specific input for this area here. When it says area, what type of area does it mean?
The area to the left.
So that'll be a left area. Who comes to mind when we say that?
Beyonce.
Yeah, you get it. To the left.
Yep. To the left. Yeah.
To the left. Yeah. Okay. So the area to the left of what? Area to the left of the z-score that you desire. So if this is the z-score we desire, then all of this that I'm doing in the lime green is the area to the left of it. So we got to figure out what that is. Well, in that middle area, there's 95%, plus we've got that little tail of 2.5%. So what's the total area to the left of our desired z-score?
So that's going to be like 97.5 or 0.975.
Yeah, 97.5%, which in decimal form is 0.975. And then we want to put the mean, which is 0 right now, and the standard deviation, which is 1 right now, because we're on the standard normal curve. And this will come out to be 1 point, what? It's something, it's almost 2. Can you do it for me?
Yeah. I got 1.959.
Okay. Could we call it?
Yeah.
Let's call it 1.96.
Okay.
Okay. And see how that is just a little bit shy of 2. An empirical rule told us that like 2 standard deviations away, we'd have 95%. And again, that was a rounding. And now we can just be a little more accurate. Wasn't that cute? Okay. What we're going to find when we get to our example is that we can actually label these to be relevant to our confidence interval discussion. So we'll come back to that in a bit. Let's talk confidence intervals. So if we're going to create a confidence interval around, first of all, what is a confidence interval? I'm getting ahead of myself.
A confidence interval is our level of confidence in that the population value is found within the boundaries that we found.
Right. So we're interested in finding, let's say, for example, for the population mean. So like we want to know for a population, what is the mean? But we can't access the whole population. So, ew, that was a creepy circle. Sorry, that was offensive. So we get a sample and we get a sample mean. And that's called our point estimate. So we use X bar, the sample mean, to approximate the population mean, but we always give ourselves a little wiggle room. Do you remember what we call this thing that we swing around both sides?
The margin of error.
Yes. So that's the margin of error. So you're taking your point estimate plus or minus your margin of error. And if we're talking about a population mean setting, then this looks like your what's called a critical value. And that's going to play back into our warm-up. Times the known population standard deviation over root n. And the good news is if we're learning from home, we don't have to memorize. We can just have these handy. The hard part is just knowing how to use these. And there are other videos really diving deeper into like the confidence intervals, where this formula comes from, how it's built. Right now, you and me are going to focus more on this little n in here. This sample size is going to be of interest to us. I'm going to give it its own fancy color for today. It's going to be a nice calming lavender.
Oh, yeah. I like that.
Very zen. I can smell it. So we're going to be very interested in that. And our goal is going to be, we want this margin of error to be within a certain like value. You don't want to just say that here's your point estimate plus or minus like whatever. You don't want a big old interval that's useless, right? Like if I was going to tell you your grade like last semester, suppose I was like, oh, Grace, your grade in the class was like a 70 plus or minus 30%.
Yeah.
You would have been like, okay, so I could have gotten like a 40% or I could have gotten 100% in the class. Like that's a really big, like almost useless interval. You don't know if you failed or got an A.
Yeah,
right?
Yeah.
So you'd like it better if I shrunk that down, right?
Okay.
Yep. So what you and me are going to talk about today is all about wanting that margin of error to be within a certain size and how big a sample we need to get before we even start our study to ensure that that happens. That's the goal. So what I like to point out before we dive into it is just the formulas that we're going to see are not new formulas to memorize. They are coming from this confidence interval formula that you know and hopefully love. And all we're saying is this is the margin of error. So if I just write that nicely, I'll just use the color here to be dramatic. The margin of error is that part, the critical value times what's called the standard error.
Okay.
Now, if you tell me like you have a certain margin of error that you want, I can like substitute that in, and then I can do some algebra and solve this equation for n and tell you the n that you need to make that happen. So all we do next is solve for n. Okay, and then what's the last move to solve for n?
The last move, you'd have to square both sides.
Right. We want to undo what's being done to n, so we square both sides. And I'm not going to ask the class to ever repeat the solving for n. We can look up this formula, but it's nice to know where they come from, and that it's not some new mysterious formula from the math gods. It's just our margin of error formula rearranged, right?
Yeah.
Okay.
Yep.
So this is the case if we're talking about means. I think we will get to that today, but we're actually going to start with proportions. You and me on our first problem here is about a proportion, not a mean. So we need to go through the same process for that very quickly, just to refresh our memory. So if we're talking about a confidence interval for a proportion, remember this is when in a population, you want to know what the population proportion is, but you can't get it. So what's the next best thing?
Like the sample proportion.
So then we say, okay, well, if we don't know the population proportion, let's just use the sample one. It's the next best thing. But again, we're going to say, but give ourselves some wiggle room. Let's have that margin of error. And in this case, again, in previous videos, we have discussed in more detail where this formula comes from, but we're going to use it now. In this scenario, what we'll have is that we have the critical value still times the square root of our sample proportion times, and do you remember what I use Q hat? What am I talking about when I say that?
Q hat is just 1 minus P hat.
Correct. Nice. That just, it saves me like a tiny bit of writing, and anytime I can save myself like a half a second, I'm going to go for it. So again, if we're in a scenario where you're like, look, I want that margin of error to be a certain size, then I'm like, cool, guess what? The margin of error is all of this stuff. So if I take and state for myself, the margin of error is all of this, and you tell me what you want that margin of error to be, I can solve this again for n and tell you how big a sample you need to make that happen before you even start your study. So quickly, one more time, let's do some algebra. Okay, so you tell me the margin of error you want. I'll substitute it in there, and I will tell you what sample size you're going to need in your study. Cool.
Okay, so for this, Netflix plans to sample customers to learn what series recommendations to make to users who have watched Schitt's Creek. They plan to construct a 95% confidence interval for the proportion of users who liked Schitt's Creek, who also liked Arrested Development. In Netflix's previous study, this proportion was 68%. Estimate the sample size needed so that a 95% confidence interval will have a margin of error of 0.06.
Awesome. And as you read that, I highlighted a few key things. So help me break down what we highlighted. So our confidence level is going to be what?
Is going to be that 95% or 0.95.
Yeah, in our calculations, we'll put it in decimal form. And then what's the symbol for the 68%? That was in a previous sample.
So that's going to be the p hat.
Yeah, so p hat equals 0.68. So that's picking apart this given info is really important. Mm-hmm. What are we calling this 0.06?
So that's our E value, the margin of error.
And I call it capital E. That's the symbol I use for margin of error. Some texts use an M. I don't like M because I think of that as like slope when y equals mx plus b. It doesn't matter. Just follow the notation of whatever you're working with, but call it something. And what are we asked to find here?
So we're asked to find the sample size.
So estimate the sample size needed. So what we want is n equals something, right?
Yeah.
Okay. That's the big thing. People are always saying, oh, I'm so intimidated by word problems. And I just say, you know, if you can break it down and say, what are you given and what do you want? That's like the whole thing.
Yeah.
And then we know the formula for that. So then based on our work on the previous pages, can you remind me what is the formula for our sample size in a proportion setting?
So it's going to be n equals p hat times q hat, and then like parentheses, the critical value, over the margin of error squared.
Cool. And that's the margin of error that you just like desire to have. So now you and me are just going to sub in what we know right off the bat. So talk to me. What do we know that we can sub in right away?
So we know that p hat is 0.68.
Cool. And if p hat's 0.68, can we find q hat?
Q hat is 1 minus p hat.
Perfect. So in this case,
it would be 1 minus 0.68. So it would be 0.32 is our q hat.
Right. If there's a 68% chance it's going to rain, there's a 32% chance it's not going to rain, right? Okay. What else do we know right off the bat?
So we know our margin of error is 0.06.
Perfect. That's what we desire. So we're going to put that right in and say we want that to be 0.06. Okay. Okay. So the last thing that we really need to find is that critical value. That's where most of our work is going to be. How do we find the critical value? What does that trace back to?
That goes back to the confidence level.
Exactly. Okay, so if we know that the confidence level is 95%, what is what we're calling alpha?
So alpha would be 1 minus the confidence level.
Correct. So 1 minus the confidence level. And that's actually also the probability of making a type 1 error. And it's called the level of significance for those of you ready for some vocab. And that would be 5%. And this kind of should start looking familiar. And for some reason, I'm always like, hey guys, let's divide that alpha by 2. If you take 5% and you divide it by 2, what do we get?
You get 0.025.
Yeah, and aren't these numbers kind of together looking familiar from a little bit earlier?
Yes, yep, from our warm-up.
Yes, so if we go back to our warm-up, let's just go right back to this picture. It's like we were starting by saying, here's our confidence level. So this is alpha, and this is alpha over 2. Okay, so I'm going to back that up again and just go along with the picture with it. Let me use the correct color. All right. So our confidence level, you can kind of picture it as being your middle area. A confidence level is two-sided. So you have the center, and then you go around this side, you go around this side, and it's symmetrical. So it's like this middle area. So picture that as like your confidence level. And then the alpha is the leftover. So what you have left to share between the two tails. And then the alpha over 2 is what each tail actually gets, right? When you do divide it by 2. Isn't that kind of cute to see the picture with it?
Yeah, definitely like solidifies it, you know?
Yeah. And then that z-score is actually our critical value. It's the z-value such that the area to its right is alpha over 2. And I know it's weird that I'm talking about the area to the right because I'm usually like, Beyonce, area to the left. But that subscript means right area. So we're just referring to, when we state that little subscript, we're talking about this area to the right. But if the area to the right is 0.025, the area to the left is 0.975. Lots of complement action in here. So what we actually just found here, notice how if the right area is 0.025, the left area is 0.975. See how those would add up to 1?
Yeah.
Yeah, so you can basically just take 1 minus alpha over 2 and you get what you put into inverse norm. So we actually did part of the work for our problem already down here with a little visual aid. So our critical value is 1.96. And I think that's always kind of fun to find. So I'm going to show it. Z sub alpha over 2 is Z sub 0.025. And so without having to draw the picture every time, you just know I want a z-score. So I want a boundary along the horizontal axis. I know the area. The subscript means the right area. The function wants the left area. So remind me of our inputs here.
So if we're looking at the left area, it would be 0.975.
Mm-hmm. And then
sorry,
I got excited.
0. No, you're good.
I'm excited. I want to do it. Okay, let's sub this in. And then we do need to go to the calculator and do this all in one swoop. So let's both do it.
Okay.
Let's both do it and see if we agree.
All right.
So all at once. So take 0.68 times 0.32 times parenthesis 1.96 divided by 0.06 and square it.
Okay, I got that as well. 232.
Cool. All right, so 232.20 like 33778. Okay, but N, remember, this is a sample size. This is going to be people, right? So is there such thing as 232.203337? Whatever, you get it.
Yeah, no.
Okay, so if we were going to round this, traditional rounding, we would just call that 232. Do you agree?
Yeah.
But what are we actually going to do in this scenario?
But for this, we have to round up to 233.
Right. And so what we're doing is we're selecting the next integer, the next larger integer. We're not actually doing a traditional rounding. Notice I'm going all the way up to 233, even though that's not how we would round that number if we were traditionally rounding. The reason for this is that if your sample size goes down, your margin of error goes up. So knowing that fact, our formula here, our work tells us 232 is not big enough to keep our margin of error within 0.06. So if we round that down to 232, so if N goes down from what we think we should get, then that margin of error is going to go bigger than 0.06. That's going to tweak that margin of error. So we're going to be outside of that error that we want. So long story short, we always choose the next largest integer when we're looking for sample size. Cool. We nailed it.
Yay.
All right. Okay, that was all well and good because we had previous study information. So they let us know, like in the past, in the previous study, we knew what p hat was. But at some point, you got to do a first study, right?
Mm-hmm. Yeah.
By the way, have you watched Arrested Development?
Yeah, I haven't finished, but I have watched it.
Oh my God, I love that one. That one's been a favorite for like, I don't know, a decade and a half. So
yeah,
good.
no, it's so good. It's so funny.
So good. Okay, so let's look now. So they did a previous study on Arrested Development, but there's a newer show that they haven't done a study on. If people liked Schitt's Creek, would they like this other newer show? Have you watched this, Kim's Convenience, yet?
Okay, see, I've also started this, but haven't finished it.
It's cute, right?
It is. No, I like it. Yeah, it's nice.
It's cute. It's not quite as funny like as Schitt's Creek, but it's got some cute little funny stuff in it. I like it.
Yeah. Yeah.
I finished the whole thing, so I do recommend.
Okay. Let's catch up.
Yeah. All right. So take us away on this one and help me with what we're going to do if it's our first time doing one of these.
Okay, so Netflix plans to sample customers to learn more about what series recommendations to make to users who have watched Schitt's Creek. They plan to construct a 95% confidence interval for the proportion of users who like Schitt's Creek who also liked Kim's Convenience. There's no previous data to utilize regarding the show Kim's Convenience. Estimate the sample size needed so that a 95% confidence interval will have a margin of error of 0.06.
Cool. So we're still wanting the same margin of error. Still same confidence level. That makes our life easy. And what is this problem asking us to look for?
So we want the sample size again for a confidence level of 95 or interval of 95%.
Right. And yeah, a confidence interval of 95% has a confidence level of 95%. So you're absolutely right. Kind of almost look at those. And the good news with that is we already did the work for it up here. So we already know if the confidence level is 95%, then showing all of our work, our critical value ends up being about 1.96. Can we just agree on that based on our warm up and our previous work? So that's done for us. Where things are a little harder here is, okay, we got the same formula as above. So in the last example, you gave me this formula. Since we still want n, we're going to use that same formula. What's the hiccup this time, though?
They don't give us a p-hat or a proportion.
Yeah, we don't have a previous study, so we don't have a previous sample proportion p-hat. Yeah. So what do we do? So
we can use 0.5.
Okay, so when there's no previous data, we actually use p-hat equals 0.5. And this isn't arbitrary. Like it kind of feels just like, all right, well then cut it in half, 50-50, right? P-hat's 0.5, Q-hat's it feels like that's what happened, but this is actually like the worst case scenario. So it's the formula here is it's parabolic. So we're actually looking at that top vertex of a parabola. If you're into algebra, we're looking at the maximum. So we're making n, we're erring on the side of caution, and our n is going to be a little larger than it probably needs to be because we have to be careful since we don't have any experience yet.
You're simply the best, better than all the rest, better than anyone I've ever met. And I'm stuck on your heart, I hang on every word you say, will tear us apart.
Long story short, again, what people really care about is, well, what do I do? You put in 0.5, but there is nice mathematical reasoning for that. So if p-hat's 0.5, what is q-hat?
Q-hat's also going to be 0.5.
And then do we know the other pieces?
Yeah, we do.
What do we got?
The critical value is going to be 1.96 still. And our margin of error is 0.06 again.
Correct. And now we just go to our calculators again. Let's do it.
All right.
0.5 times 0.5 times, don't forget your parentheses, 1.96 divided by 0.06. Square. You're better than me. You always say 0.06, like you're polite and you put the 0 before the I'm like, I'm so rude. I don't have time for that.
That's funny. Yep, I got 266.7.
266.7, repeating, right? So that kind of just keeps going.
Yeah.
So what are we going to use for n?
So we're gonna use 267.
Which actually would be how we round that number. But again, it's nice to see it on the previous one, how even if the next, like the decimal isn't like bigger than 5, and you wouldn't usually round up, you still select the next integer up. Cool. Yeah. Doable? Yep. Okay, now those problems though were all about proportions. What if we back up and we do something like when we started our chat today, and we're going to look at talking about means. We'll have a slightly different formula, right, for that? Yeah. So let's see what's up here. Help me out.
So researchers want to determine the mean number of hours that users age 18 to 28 spend watching Schitt's Creek on Netflix. From previous studies, it is known that the number of hours is normally distributed with a standard deviation of 2.5 hours. How many users age 18 to 28 must be included in the study so that a 9-day confidence interval will have a margin of error of 0.5 hours?
Okay. Great. So we're given a lot of information here. Firstly, I always like to ask myself, what is it that the problem is asking us for? What do we want?
We want to know how many users must be included in the study.
Right. So again, we're after n, aren't we? It's tempting to get lost in it and be like, wait, am I constructing a confidence interval? Do I need to find an average? Like there's a lot in here. So you got to look at the question. Like, what do I want? I want to know the number of users. That's n. I got to find n. And there's a formula for that. So then you look at your notes or you do the fun algebra for it and go back and you take a look and say, oh, there she is. Okay, so help me out with the formula. I know you have these like tattooed on the inside of your brain because you're a math nerd like me. So what is n in this scenario? Because we're talking about means this time.
Yeah. So that's going to be in parentheses, it's going to be the z alpha 2, the critical value, times this standard deviation over our margin of error squared.
So nothing we can't handle. We just got to know what all those pieces are. So were we given some of those pieces? If we go back and look at those little highlightings, what do you notice? What's the purple, the dark purple?
So the purple is our standard deviation.
Yeah, and we know that. Yeah, good. Okay, so we can sub that in. What else do we know that we can sub right in?
We know the margin of error is 0.5.
Yeah, we've got a desired margin of error this time again. So 0.5 can go down below. I'll put the 0 just for you.
Thanks so much.
I know. I want you to be able to breathe. The only thing we need now is the critical value. How do we find the critical value?
So that through the confidence interval, that 98%.
Right. So the confidence level, just like you said, was given to be the 98%. Okay, I'm going to do like a little quickie picture, not like a perfect one, but just like to help us always do this. Picture that bell-shaped curve. Your confidence level is in that middle. So you've got 98% in here. Alpha is what you would share between the two tails. So what would alpha be?
That's going to be 0.02.
Yeah, 2%. Alpha over 2 is what each tail will inevitably end up getting.
So that's 0.01.
So we'd have 1% in here, 1% in here. That little percent looks creepy. Hold on. You get the idea. Each tail has 1% in it. So that's your alpha over 2. So your critical value is the z-score such that you have that little 1% to the right, where this is our critical value, this boundary right here. Okay, so if the error to the right is 1%, we know we're going to use inverse norm here. Help me with our input.
So our first input is going to be that 0.99, the area to the left.
Right. If the area to the right is 1%, the area to the left is 100 minus that. 100% minus 1% is 99%. You can also see in your picture the 98 in blue plus the 1 in orange to the left. So all of this is 99%, right? A lot of ways to do it. A lot of people just look at that subscript and say that's 1%. So I'm going to go 1 minus that in here, which is indeed what you just said. And then mean and standard deviation?
0 and 1.
I'll let you do it this time because I stole your thunder last time. What do we get for this? Should be kind of far out there. What do we get for that? Can you help me with that?
So we get 2.326.
2.32. I mean, you could call it 2.33 if you want. A lot of times people traditionally round z-scores to 2 decimals, but hey, let's go for it. Let's use the 3 decimals because we got it. So let's do it. So we're just stuffing that in. These problems become just real, like mathematicians call them plug and chug because you're just stubbing in pieces. And so they become pretty straightforward. Let's do this whole thing. Don't forget the parentheses before you square it in our calculator. So we'll both do it. Make sure we get the same thing.
Okay. Yep, I got 135.26 also.
135.26. So what are we going to use for our sample size?
So we're going to use 136.
Yep. Next size up. Now, even though if you were to round that number to the nearest integer, that would be 135, right? But we don't want to take it down because if we take n down, margin of error goes up and we're outside of what we wanted for that. So always go up to the next integer on these. Nice. A little keyword, like how did we know which formula to use each time? Because you gave me this formula for this one. We used it again here. And the reason we knew that was the formula we wanted is we were talking about proportions. So anytime you're talking about proportions, you need to be working with the scenario about proportions. And that's where this equation and formula was born of. And then on this next one, we were talking about means. So if you're talking about a mean, you need to be working with a formula that was born of a mean situation. And so that's where this equation came into play. So that's what we just want to keep in mind when we get to our quiz and it's a mixed bag of all the sections, because like 8.1 and 8.2 are about means, but then 8.3 is about proportions. So when you're doing your homework, it's easy to keep it straight, but when you get to the quiz, you want to be able to identify which is the right one to use.
Yeah.
And then when you're done, you can celebrate by watching David and Alexis.
Yes.
All right. Well, I know they're going to be coming to me for Zoom Live help and they'll come to you for Zoom Live help. So we'll both be ready to help them out with all of this. Okay. All right. Well, I'll see you next time.
Okay. Bye.
Bye.
Hi, my name is Alexis Rose, represented by Alexis Rose Talent.
Okay, what are you going to be singing for us today, Alexis?
I have chosen to perform the title track off of my critically reviewed limited reality series, A Little Bit Alexis.
Ooh.
Feel free to sing along if you know the words.
Okay.
Are you ready? Let's do it. I'm a Lamborghini. I'm a Hollywood star. I'm a little bit tipsy when I drive my car. I'm expensive sushi. I'm a cute, huge yacht. I'm a little bit single. room, bitches.